Hi, everybody. Mr. Colford here, and today we're going to talk about hydrogen fuel cells. Now, this goes along with one of the lessons that we're going to be covering. This is within the unit 1.3 energy applications, and more specifically, it's going to go ahead and kick off a couple of activities that we do. The first of which was activity 1.3.1, which is solar hydrogen systems, which is going to be kind of cool. What we're going to do is we're going to take a couple of X motors. We're going to create a basic vehicle. We're going to go ahead and wire them up to a solar panel and to a fuel cell and see if we can't get them to go fast. So this will be kind of cool, and I'm looking forward to it. But hydrogen is actually one of the coolest things. One of the things that I like to talk about the most. So let's take a look at, first off, trends in fuel use. Now, over time, and it's interesting to note here that fuels actually developed to contain more hydrogen. And the higher the percentage of hydrogen content, the less other products we have. So, of course, when you have some type of oil or coal that you're burning, you have a high amount of carbon dioxide that's being uh, released into the atmosphere. But the more hydrocarbon fuels that we create, the less emissions of carbon dioxide we're seeing in those. So it's kind of cool. Now, taking a look at history, back in the 19th century, we had, steam engines, which was, the century of steam engines. We had a lot of that taking place. A lot of different organizations, energy companies, and even automobile manufacturers had different types of fuel cells that they were creating. And steam engines were great, but it just didn't have the power of the internal combustion engine. So in the 20th century, we ended up going in that direction. Now we have technology in the 21st century to develop more of these fuel cells, and especially fuel cells that are stacked together that allow an engine to become a little more efficient or a lot more efficient, just by using a couple of hydrogen molecules, which is pretty cool. So, in continuing on, it's got kind of a cool history, and it starts in 1839. We've got Sir William Grove. He was a British scientist and a lawyer, and his principle was actually discovered by accident. What he was doing, he was doing an electrolysis experiment. And what an electrolysis experiment is you go ahead and put an anode and a cathode into a jar of water, and you pass a current through it, and it breaks those molecules apart and breaks them into hydrogen and oxygen. And it was kind of cool. And he was doing that, but when he disconnected the connection, the current, he noticed that it started flowing in an opposite direction without even being connected to the battery. So it started consuming the gases like hydrogen and oxygen together, and it started creating a type of current. And he found that the current that was being produced was equal to 1 volt, which was kind of cool. And so he called this device a gas battery, and his gas battery consisted of these platinum electrodes placed in test tubes of hydrogen and oxygen, immersed in a bath of diluted sulfuric acid. Now, this experiment can actually be done a couple of different ways. It can be sulfuric acid or diluted sulfuric acid. It could be even methane contains hydrogen. You could do it with just plain water. But either way, the opposite, using hydrogen and oxygen specifically, will create that chain reaction, which is kind of cool. Now, because it wasn't practical during that time period, and there were a couple of problems since he was using um, some type of acid as the medium between the two. There was a lot of instability, corrosion, that type of stuff, and so it it wasn't researched as much, but it became kind of a footnote in his notebook that he then passed on. Now, later on, there was a significant development work on fuel cells that began in the late 1930s or the early 1930s, about 100 years later, by Sir Francis Bacon. He was a chemical engineer at Cambridge University, and in about 1950s, I want to say, Bacon he started producing some of the first practical fuel cells, which was kind of cool. He picked up notes from his predecessor and started developing some really cool things. Now, for this one, he actually used an alkaline fuel cell instead of the sulfuric acid or the diluted sulfuric acid that was used before. And so the alkaline electrolyte created kind of a larger reaction. So the electrodes were constructed of like this porous nickel powder. So the gases could then diffuse through the electrodes to be in contact with the aqueous electrolyte on the other side. Now, this increased the contact area between the electrodes, the gases, and the electrolyte, which meant that they increased the power density of the fuel cell. So, in addition to the use of nickel, that was a lot less expensive than platinum. So, they went ahead and did that. Now, in this picture, you can see an assistant mounting a plate onto the side of Francis Bacon's fuel cell stack, or Sir Francis Bacon's fuel cell stack, which is kind of cool. But there's some type of reaction that happens here, and we can talk about that in class if you really want to. But so later on, we actually had NASA pick this up, NASA Space Shuttle fuel cell. They did significant research into it. So the Bacon fuel cell was actually modified a little bit in the 1960s as a method to supply drinking water as well as electricity for the astronauts aboard the Apollo space missions. So very simple, just had a couple of the electrolyte solution, the anode, the cathode, the hydrogen. It's a lot lighter than water itself, and so they went ahead and set that up, and it provided two things in the reaction: fresh water um, and the electricity that they could use. Unfortunately, it used a lot of water, or not water, but oxygen, which was difficult to get into space as well. So the Space Shuttle Orbiter fuel cell has been produced since the 1970s and still used in the United States. It produces about 12 kilowatts of electricity, weighs about 202 pounds, and it occupies a space of like 4.6 feet. Um, so what's going on in this thing is that the alkaline fuel cells um, offer an advantage of high voltage output per cell, and each of the cells in the space shuttle has an operating voltage of about it's less than 1 volt, but it's pretty close to a volt. It's like zero point 0.8 something. And that non-precious material can actually be used as electrodes. So the primary disadvantage of an alkaline fuel cell for terrestrial applications is that both the carbon dioxide that's released from this can actually deteriorate or poison the electrolyte. So carbon dioxide, which is present in both the atmosphere as well as the reformat, the hydrogen-rich gas produced from the reformation of the hydrocarbon fuels, it reacts with the hydrogen ion in the electrolyte to form a carbonate. So it actually reduces the hydrogen ion concentration in the electrolyte, which reduces the concentration, and it inhibits the ability of the fuel cell to generate any type of current. So it actually exponentially decreases its efficiency over time. So there is quite a complexity of isolating the carbon dioxide from the alkaline electrolyte for terrestrial applications. Most fuel cells that are being developed today actually have their focused they focus their attention on developing new types of fuel cells, including electrolytes other than alkaline. Alkaline's great, but unfortunately, we still have that release of carbon dioxide in that type of reaction. Now, just in the past couple of years, we've seen a couple of fuel cell cars pop up. There's the Nicar 5. This was developed in about, I don't know, about the 1980s, or it was originally proposed in the 1980s. There was a company called Ballard Power that was based out of Vancouver, Canada. And they went ahead and worked on a contract from the Canadian Department of National Defense, and they made a significant breakthrough in these fuel cells. So Jonathan Matthey from the UK developed what's called a PEM fuel cell, or a PEMFC. And it stands for protein exchange membrane fuel cells, which actually had a significant increase in power density. So from this breakthrough, it was actually recognized that fuel cells could be made small, powerful, inexpensive, enough to replace the conventional power technologies. Now, the California Low Emissions Vehicle Program, a program from the California Air Resources Board, or CARB, has been a large incentive for automakers to develop fuel cell automobiles. So the program requires that it required that beginning in 2003, 10% of passenger cars delivered in for sale in California had to be zero emission vehicles. And so it had to be some kind of hybrid car, electric car, fuel cell car, whatever it was. It required that there was zero emission vehicles on the roads, and these are called ZEVs. Now, automobiles powered by fuel cells met these requirements, and to date, 7 of the world's 10 leading auto manufacturers plan to introduce the fuel cell automobiles beginning, well, it kind of took its place back in 2003 to 2005. Now, the Nicar shown here, it's just a prototype. It was made by 2 different companies, Daimler and Chrysler. And this is an automobile that's fueled with methanol. And it has a top speed of 90 miles an hour. And they hoped that with the coming years that there would be plans to do buses, trucks, trains, and all kinds of vehicles with these fuel cell engines. And in fact, in 2002, there were 30 buses that were commercially introduced to Europe. However, that didn't quite pick up traction, and we're still trying to promote fuel cell cars and push them in that direction. Okay, so this is when we're talking about the application for fuel cells, um, we're seeing a constant energy demand increase throughout the world, not just the United States. In Canada, the electrical energy demand is growing at a rate of like 2.6%. In America, the electrical energy demand is growing a little less than that, actually. It's about 2.4%. In developing countries, electrical demand is growing at an annual rate of 6% each year. Now, you got to ask yourself, how can these demands be met responsibly and safely? And so we've got to figure out a way, because right now our main producer of energy is a fossil fuel. And a fossil fuel is going to last forever. It's going to, the more we harvest, the less we have. Eventually, we're going to reach the point where we don't have it anymore. We can't produce it. And so, we've got to find alternates. And so there are a lot of problems that are associated with building new power plants, financial, environmental, all that good stuff. And fuel cells have shown that these power plants can actually produce high quality, reliable power, depending on the type of fuel that the fuel cell uses. And so, like we said, if we end up using one over the other, it produces carbon emissions, and then we're kind of back in the same boat. So shown right here in this picture, you're going to see a prototype fuel cell. It's distributed by a particular power plant created by Ballard Power, as you can see on the outside there. Now, this unit was actually commissioned by BC Hydro Grid, and it provides 250 kilowatts of electricity, which is huge in the amount of fuel and heat from natural gas. And this is enough to provide heat and electricity to a community of about 50 homes. And it's fairly large, but when you consider that this is being fueled just by some type of fuel cell, that's pretty cool. And when you think about recovery and recover like help efforts after a disaster or something, this can easily be transported to hospitals or remote locations to provide energy on a short-term basis, and it's completely off the grid, so it's kind of cool. Now, Ballard planned to introduce the first commercial fuel cell back in 2003, and they did for the most part, but they were fairly uncommon. They were really, really expensive, and that's kind of the thing that has hurt fuel cells. In the very beginning of any type of natural energy, you're going to have really high costs, and unfortunately, you're going to have to convince those people with the money that they need to make that investment. Now, here's another fuel cell. This fuel cell power plant is also being developed by several manufacturers to provide electricity and heat to a single family home. Now, this is fueled either by natural gas or propane, and these fuel cell power plants will be able to power a home independently off the grid. So it's kind of cool. So this one, you'll be able to plug in the power based in Latham, New York, or rather, Plug Power, based in Latham, New York, has developed a new fuel cell power plant that supplies 7 kilowatts of electricity and heat using either natural gas or propane as a fuel. So that's enough to power or to supply the electrical demand of a modern, energy efficient home. Initially, these fuel cell power plants will be grid paralleled, so they can increase their their voltage over time. And eventually, they're going to be grid dependent or independent. So you're just going to be able to unplug them. So this is also kind of a cool next step in fuel cells. All right, so this one here is a portable fuel cell, and there are several manufacturers that are kind of developing these portable fuel cell power supplies. Unfortunately, these are still fairly bulky. Even though they're pretty efficient, these are developed for use for like laptops, cell phones, remote road signs, lighting, that kind of stuff. And unfortunately, they're just big. They're just too big. Now these ones, they are fairly dense, so they have a lot of volume and weight. The fuel cell portable power packs, they can be a little bit lighter than like a battery, but they still have quite a bit of weight to them. So I guess this one particular one actually produces 50 watts of portable fuel with a metal hydride storage. These ones do have a PEM fuel cell, which is pretty cool. PEM, just protein exchange membrane fuel cell. It allows the energy to kind of pass through it, or the hydrogen to pass through it, but the energy has to go around the membrane. And so while it's going around it, we can capture that. If you stack the fuel cells, then you'll be able to harness the energy a little bit more efficiently. So, with the advent of this process, recharging batteries probably isn't going to be an issue now. We also have the ability to process electrolysis via something like solar energy, which fills a container full of hydrogen. The hydrogen then is used to pass through the fuel cells, and you basically have this fuel cell that can last indefinitely without decomposing or breaking down. Now let's talk about some of the different types of fuel cells. Now I've talked about the PEMFC, which is like a polymer electrolyte or protein exchange membrane fuel cell. Even though that's kind of one of the most promising things, it's one of the less efficient ones. This one literally has an input of oxygen and hydrogen, and it has an output of basically H2O. They come together, and that's what it is. And so it doesn't do any environmental damage, which is kind of cool. Now, there is a low temperature fuel cell that's included, the alkaline fuel cell, which is the AFC. Um, and that one's kind of cool as well, a little more efficient, but again, it uses that alkaline fuel, which can create some type of offset of carbon dioxide. Now, the PMFC, we've talked about that. You can also use natural gas, biogases, methanol, or propane in this process. Most of the time, even if it's like methane, methane actually contains 6 hydrogen molecules in it, compared to water, which only has 2. So, yeah, that can be a little more efficient, but again, it can also, uh, release carbon dioxide. Now, in high temperatures, we've got fuel cells that are included in the molten carbon fuel cell, like the MCFC and the solid state oxide fuel cell, SOFC. And these fuels can actually offer the advantage that they can use either natural gas or untreated coal as a gas without the fuel directly, or without the use of reformer through the process called um, direct internal reforming. Now, the sixth type of fuel cell in the direct methanol fuel cell is called the direct methanol fuel cell, or DMFC. Um, and it's also without low temperature fuel cell, but it can be used. It can use methanol as a fuel directly without the need of reforming. The primary limitation of the direct methanol fuel cell is that the rate of reaction in the anode is actually pretty slow. Now, this results in a very low operating voltage output. For certain applications like portable power, the direct methanol fuel cell could be ideal, but for other things, it may not be as ideal. So now let's take a look at some of the chemical reactions here. Let's say we've got some hydrogen and we want to pass it through some type of membrane. Well, this is the kind of the way that we do it. So a fuel cells device that through an electrochemical process converts hydrogen and oxygen directly into water. In this process, energy is released in the form of electricity and heat. The chemical process is electrolysis in reverse. In the PEMFC, hydrogen molecules are oxidized at the anode to positively charge hydrogen ions, protons, and releasing electrons into the cathode via an external electric load. So basically, what it's doing is it's introduced to this protein exchange membrane. The membrane won't allow the electricity to pass through it. In fact, if we go to the next slide here, you can kind of see the reaction here. So you've got the hydrogen that's introduced into the system. You've got the electric polymer, or the electrolyte polymer that's in between here. And then you've got the oxygen that's introduced to the outside. And oxygen's pretty much everywhere. So you have the hydrogen that comes in, and it's automatically attracted to the oxygen. So it wants to pass through that, and it can. And so it goes through that. But unfortunately, the electrons, the protons, they can't go through there. And so what we've got over here is an anode, and that anode is the direct connection to the other side, but it has to go around the membrane. And so the anode travels through the wiring. It goes into the load, whatever you're using it for. Say you're plugging in a flashlight or a light bulb, whatever, and then it continues on throughout and goes to the cathode on the other side. There it reattaches itself to the hydrogen, and then the hydrogen and oxygen combine to create water. This is literally power with an output of water, which is pretty amazing. Now, if we take a close look at the membrane electrode assembly, or the MEA, this is what we're kind of seeing. So you'll see that we've got the hydrogen that again passes through it, but as it goes through this solution, it drops that little electrode or a proton or electron, and that electron gets filtered out through the carbon cloth that's over the top of it. These are all attracted to each other, and they go ahead and pass between these um, to the other side, but we can go ahead and harness them as they're passing through. Okay, taking a look at the PEM, or the polymer electrolyte membrane. The membrane is a fuel cell of like 50 and 175 microns thick. That's about 2 to 7 sheets of paper, roughly, like a stack of papers. It's produced in sheets which can then be cut down to the required size that you need them. Unfortunately, these are so expensive because they're hard to manufacture long term. So the electrolyte membrane consists of PTFE. It's a polytetrafluoro. I'm not going to do it justice. Polytetrafluoroethylene, uh, which is kind of a chain more commonly called Teflon. Uh, uh, so that's what we commonly use it for. And what you notice from Teflon works really well. It has a specific chain that acts like a hydrophobic. And with the hydrophobic, it repels water. Um, the sulfonite side chains are then highly hydrophobic. They attract water, but the Teflon side doesn't. So with that, whenever you see some type of hydrophobic, you're going to know that it acts as an insulator for electricity as well. And so the hydrophobic regions absorb a large quantity of water within these, or hydrophilic, sorry, regions. They absorb the water. And the hydrophobic water resists, or the hydrophobic regions um, will resist the water. Now, within the hydrated regions, the hydrogen ions from the sulfonic acid are able to move, creating the ability for the material to transfer the ions from one side of the membrane to the other. Now, for this reason, the hydrated regions must be as large as possible. This is kind of the downside. You need a lot of surface area, even if it's like a small one, a tiny little fuel cell. You still need quite a bit of surface area to take care of it. Like I said, these are produced in sheets, so they're really thin. But if you stack those sheets on top of each other, now you have the ability to harvest it a little more efficiently. Now, looking at the thermodynamics of a PEMFC, we can work through the calculations that we see for ideal cell voltage at a room temperature, which is about 1.23 volts. However, the fuel cell heats up to an operating temperature of about 80 degrees centigrade. The ideal cell voltage then drops to 1.8 volts. So whenever you have heat, you have less efficient means of obtaining electricity. So more factors are involved in practical fuel cells, which reduce the cell voltage considerably. The temperature that these tend to operate at is kind of an issue as well. Now, because there's such a process that people have to go through to produce these, they're also incredibly expensive. So if you're looking at like even a centimeter square of this PEMFC, you're probably going to pay about $80 for it. So not a whole lot that you're getting for a lot of money. Okay, now we can see here the characteristic curve of the fuel cells, the characteristic curve of fuel cells relationship between the current density and the cell voltage. And so you'll notice a sharp fall from the ideal cell voltage immediately following an open circuit. This is to follow by somewhat linear decline in the cell voltage. This is followed by a rapid drop off in the cell voltage. So you'll notice right here, it starts tapering off. You have the ohmic losses and then the concentration losses, and then it just drops completely off. So the primary factors that are affecting the curve are actually listed down here. Now, each of these loses or losses contributes to the decline in the cell voltage. So activation losses are a result of the slow speed of the reactions taking place. Fuel crossover and internal currents is a result of the fuel which crosses through the membrane, not contributing to the chemical redox reaction, but not contributing to the production of electricity. And then we've got the ohmic losses. These are a direct relationship to the combined resistance of the various components within the fuel cell circuit. This includes the material of the electrodes, the membrane, and some of the interconnections throughout as well. And then you've got mass transport or concentration losses. Mass transport is called concentration losses, but it's a result of the reduction of the concentration of hydrogen and oxygen on the electrode surface. So, like I said, more surface area is good, less surface area is bad. So you need to hit that sweet spot in between. So most of the mass transport or the concentration loss is failure to the transport or the transportation that's required of the gases to the electrode surfaces. So you don't have as much pressure that's pushing behind those things. So careful design and all the components involving science and engineering and some technical trades. The losses can actually be minimized, resulting in fuel cells that are efficient and deliver high power density. But that's the requirement. We've got to have people that understand it, have the funding to be able to do it, and yeah, just overall more efficient designs. So the second graph over here is called the power curve. And this is the plot in the relationship between the current and the density. And the power output of the cell, it kind of peaks out right about here and then starts to decline. The maximum power point of the fuel cell can actually be determined either by plotting it on like a graph like this or by just taking a look at it as shown here. Um, Determining the equation of the curve and differentiating the equation is actually right here down at the very bottom. And we're going to talk about that too in just a little while. So, hydrogen storage. This is one of the better things that can be stored. Hydrogen is non-corrosive, and so it doesn't break down after a while. And it's interesting to compare kind of the various methods available to date for the storage of hydrogen. And we see that to store 1 kilogram of hydrogen in a compressed gas cylinder only requires 56 liters. In liquid hydrogen, not including the necessary equipment requires, in 14 liters. That's it. That's all they need. When you're talking about metal hydrate or hydrogen stored in magnesium metal hydrate containers, it only requires 9.9 liters, which is really, really cool. Now, hydrogen, like I said, because it's non corrosive, could actually be stored in those containers for a really, really long time, and they could be called on at any point. Now, this is different from like an acid battery. Acid batteries lose their power over time because they're corrosive, and corrosive batteries are going to break down very quickly in comparison. So reformers convert a hydrogen-rich fuel like natural gas, methanol, or even gasoline to pure hydrogen, plus the emission of carbon dioxide. So they work via catalytic process, combining a fuel with the water vapor at a high temperature. The result is the fuel cell automobiles are able to carry liquid fuels, and fuel cell stationary power plants can use natural gas or even propane and for the immediate future, as long as fossil fuels are available, the use of reformers is kind of the most cost-effective method of producing hydrogen. So we could still use these to produce them. Probably the most environmentally friendly, however, would be solar panels that uses an electrolyzer and then stores the hydrogen long term. And solar panels can pretty much be placed anywhere, which is kind of cool. Down here at the bottom, you're going to see algae that breaks down. Algae is another method of obtaining some type of hydrogen. Whenever algae breaks down or when it's growing, it has small amounts of methane that it produces and pushes out. So this would be a type of biological mechanism that could one day actually create an entirely different source of hydrogen and energy, which is really cool. Okay, renewable energy sources: solar cells, wind cells, hydro turbines. Um, these can all be used with an electrolyzer to create some type of fuel cell. So this is looking like this is a completely clean energy that we just haven't tapped. If those fuel cells were just a little less expensive, I think it would be a little more beneficial. But, essentially, as long as the sun shines, as long as the wind blows, as long as the rivers are flowing, we can actually have a really good, sustainable energy resource that we can actually call on when required, no matter what. Now, the benefits of the fuel cells, we've already talked about a couple of these. Fuel cells are incredibly clean. They have an offshoot of, or an output of water and water vapor. Um, they're they don't produce a whole lot of heat. Even though they do produce some heat, they don't produce a lot of it. So these things are really incredibly clean. They're also quiet. They're safe. Even though we're using hydrogen, hydrogen is volatile when it's ignited. We're not igniting hydrogen. We're actually just letting it pass through a fuel cell. And so it's really quiet. It's pretty fast. It's efficient. It's sustainable. And it's modular. So you can pretty much take it anywhere you want to. There are nothing but benefits to fuel cells, which is why I really, really love this. It's environmentally friendly. It's economical or economically friendly. There are just tons and tons of benefits to fuel cells. And unfortunately, we haven't quite gotten to that point yet. Now, when we talk about energy efficiency, we we have to consider, especially when we're talking about the energy increase in the demands on energy, we have to find other sources. Now, hydrogen's probably not the thing that's going to be the thing that gets us to the future. That's something else. But it is one of those things that can be used in conjunction with other things that will actually reduce the demand on our planet and help the planet. This is one of those things that we just kind of need to do because it's there, it's more efficient, it's environmentally friendly. There are nothing but good things to say about hydrogen fuel cells. So, continuing on, activity 1.3.1. Now you understand kind of the background around the fuel cells. We're going to use an electrolysis machine or a device to separate the oxygen and the hydrogen. And then we're going to go ahead and reintroduce that hydrogen into the electrolyzer to create a negative current. And we're going to use that to propel our cars forward. So that is coming up in the next exercise. Um, Let me know if you guys have any questions just by sending me an email at dacolford at dsdmail.net.